Hi everyone, this is going to be a recording of the webinar titled Fledermaus 2, Fledermaus Tools and Techniques, which was presented on 15 April 2011. If any of you have attended it and saw it live, you will notice that this is going to be a little bit different. Reason being, I forgot to hit the record button, so this is a post-live webinar re-recording of what we covered, and hopefully I won't forget anything. All right, so what I'm going to cover in this session, I'm going to start with a really quick overview of the Fledermaus suite. I'm going to also review Fledermaus module basics, and that will encompass a workflow review of how you get data into Fledermaus, and then a really quick demo of importing core data into Fledermaus, so gridded and ungridded data. That was covered in depth in a few of the earlier webinars, so that's why I'm going to kind of fly through that. After that, we'll have built up a nice set of data to work with, and then I'm going to move on to showing you tools and techniques within the Fledermaus module itself. So just a review of Fledermaus. The Fledermaus suite is leading 4D visualization and analysis software primarily used for marine data. We can be used for topographic data. Any kind of general XYZ data will do, but we tend to be used in the marine environment. We do 4D visualization, primarily in the ocean mapping realm. We do real-time visualization, and that's with a module called Vessel Manager. We do project management and data manipulation, do geospatial processing for multibeam sonar and LiDAR data. We also process backscatter, do route planning, and have a free viewer called iView4D, which lets you make scenes and SDs for collaboration and distribution. So not everyone who looks at your visualizations has to have Fledermaus. This is what the Fledermaus suite looks like. So this is the Start menu in Windows. At the top level, I'm looking at the Fledermaus suite folder. And then within that, I'm looking at all of the Fledermaus modules. The modules that you have available will depend on the bundle of the software that you have. Just to review the bundles of software that are available, the core of the entire suite is FM Viz 4D, and that contains Fledermaus, DMagic, Vessel Manager, OmniViewer, and FM Command. Every other bundle builds on top of that, and the bundles are really focused on particular users. So FM Hydro adds the ability to process LiDAR and multibeam data. FM Offshore adds the option to do route planning. FM Habitat has the geocoder backscatter processing, and FM Pro will have everything with the exception of FM Midwater. FM Midwater is our new water column processing module, and that's an option no matter what bundle you have. So that's always an add-on. It doesn't come included in anything. To focus on Fledermaus, Fledermaus is the entire suite of software. So we say the Fledermaus suite, and that encompasses all of these modules. Fledermaus is also the name of the main visualization module itself. So there, within the Fledermaus suite, you can see the Fledermaus module. The Fledermaus is part of every bundle. It is the core tool of the suite. We also abbreviated FM. So when you see the letters FM somewhere, that is referring to the Fledermaus module. The data that we support, so starting with ungridded data, these are point data imports that we support that you can bring in and create DTM surfaces. The core data that you bring into Fledermaus is ungridded and gridded data to create topographic and bathymetric terrain models. So for point data imports, some common ones are ASCII XYZ, GSF, HCCS, which is CARIS, or LAS, which is LiDAR data. A lot of these are proprietary formats that come from sonar manufacturers or processing or acquisition software. On the gridded side, we also bring in some pre-gridded formats, so ArcView grids, ER Mapper grids, again, gridded ASCII data, eTopo data. If you want to see all of our supported data formats, you can visit our website, and under support there is a section called data formats. You can also bring in what we call ancillary data, or extra data, and that's data to enhance your visualization. So that's things like images, vertical images, lines and points, DXF files, arc shape files, 3D models, and ENCs. We create two primary data types within the Fledermaus module. The first is a .sd file, or scientific data object file. These are also called DTMs, terrain models, surfaces, or bathymetric models. We use all of those terms interchangeably. Everything you bring into Fledermaus becomes an SD file, and what we're looking at here is a DTM SD. So that's an SD that is showing terrain. You could profile on DTMs, do things like that. The other primary file type we create is a scene file, .scene. A scene file is a group of SD files. So here we're looking at many SD files together and that have been saved in one scene. It's kind of like a package to keep everything together. Really quick workflow review. How do you get your data into the Fledermaus module? There's two methods. There's the simple workflow and project-based workflow. Simple workflow means you open the Fledermaus module and you just import things. If you're going to do the project-based style, that means you're going to use a combination of the DMagic module and the Fledermaus module. DMagic lets you organize your projects before you make SD files for visualization in Fledermaus. If you want more info on the project-based workflows or just different workflows in Fledermaus, we had an entire webinar devoted to that in July, and that's available for clients for download. Simple workflow means, what it means to us is that you can just open Fledermaus and import gridded and ungridded data directly. You can bring in your images and drape them. You can bring in scalar information. You can also export images and maps and create other products. And you're going to use a simple workflow when you just want to make a quick, nice visualization for an area, one that you probably may not be returning to. Or if you just want to quickly grid up some data for QC. So if you're out doing a survey and you want to do a quick check on your data, you can just import it directly into Fledermaus. And just a reminder that Fledermaus is the core module. All of the visualization in the entire software suite is done here. DMagic is kind of a back end of a project-based workflow. You do analysis and stuff there, but it's basically setting projects up for visualization in Fledermaus. And most of the other modules or options that are available work within Fledermaus, for example, Vessel Manager or the FMGIS integration, or they're modules that are used to get data into Fledermaus, so things like FM Midwater or Route Planner. Real basic workflow to get data into Fledermaus. This is a little simple schematic. You can start with ungridded or gridded data, so ungridded XYZ, GSF, HiPAC HS2s, or gridded data like base surfaces or eTopo data. You'll import those into the Fledermaus module. Within Fledermaus, you'll automatically create DTM SDs, and then you'll save those DTM SDs as a scene. If you want more info on this basic part of the workflow, the creation of SD files, we have an entire webinar called that focused on Fledermaus that we held in August, and again, that's available for download for clients under maintenance. All right, so I'm going to go into a demonstration. I'm going to very quickly review importing that core base data into Fledermaus. So we're going to import gridded and ungridded data. We're also going to open a Fledermaus SD that was already created, and we're going to save the scene. Again, we're going to do this really quick because this was covered in great detail in earlier webinars. All right, so I'm going to start by opening Fledermaus. The first thing I'm going to do within Fledermaus is open an SC file that was already created. So if somebody's made Fledermaus files already, to open them, you just go to File, Open Data Object Scene, and I'm going to bring in my Portsmouth files some Reason data from 2001. All right, so this is a DTM type SD. If I just move around and take a look at it, it's a nice surface model of portion of the harbor and moving up the river. This is my data object display area, and these are my data attributes. All right, so that's the first way you can bring data in. Second option is to import gridded data. So to do that, you go to Import, import gridded data. So gridded data is data that has been decimated already, that someone's run through a gridding algorithm and made into a file that just has regularly spaced points in it. For my gridded data, I'm going to bring in some XYZ data, so just a typical ASCII type of text file. This is some topo LiDAR data. So you select your file, click Open. You tell it the type of file that you're working with, and this is ASCII gridded data. You could choose your option from the pull-down menu. Click Next. You set up any variables or header lines. You set the mapping, so you just want to make sure it's mapping the right columns. You set the input coordinate system, so this is the coordinate system of the data coming in. You let it do a quick scan of your data. This is going to tell you the extents of your data as well as the dimensions of the grid that will be created. Do any Z coordinate options that you have to do if you have to invert your data. You set the output coordinate system, so the coordinate system for the SD file that's going to be created. You're going to be making a sonar or surface DTM. You give it a name, and we're going to stick with the default. And if you wanted to, you could change the color here, but we're going to leave it as such. All right, so we have a new file in our data object list called topo LiDAR. If I zoom out, you'll see that this is indeed some LiDAR data surrounding the bathymetry, and the points we're seeing there are trees, and then we're looking at some mud flats along the water's edge. All right, third way to bring data in is to bring in ungridded data. So this is your really dense data that hasn't been decimated at all yet. It usually has all of the points as collected by the sonar, or maybe it has all of the clean soundings in it. To bring in ungridded data, you go to Import and Import Ungridded Data. So I'm just going to do a couple of lines as an example. You add your files. I'll go select some ungridded data. And just has 2 lines of Consberg.all data. Click Next. The value to grid is the column that's gridded. Input coordinate system is the input coordinate system for the data, and this data is in decimal degrees, so WGS84. Output coordinate system is what you want the SD file to be in once it's created. Because my scene's in zone 19 and all of my other objects are in zone 19, I'm going to set it to zone 19 and click Next. I'm going to set my cell size to 3, and that's 3 meters. I'm going to scan the file for bounds. Just take a couple seconds to scan through. Once your scan is complete, it will tell you the bounds of your data file and also the bounds of the DTM that's going to be created from your file. Click Next. You can set your color map here if you choose. Next, you're going to be creating a surface DTM. You give it a name, so I'm going to call it Sample Kongsberg. Click Finish. And just a couple more seconds while it now grids that data. All right, and if I click on the new data object listed in the datasets list and hit the Z hotkey for zoom to object, it will take me to my section of the seafloor that I gridded out here. Now this is just 2 lines of a bigger data set. I wanted to bring that in as a demonstration, but I'm going to actually delete it now and bring in a pre-created SD file to fill in this whole portion of the bathymetry. So I'm going to remove the object and then just open a data object and bring in the SD file for that area. All right, so now I've brought in a bunch of base data. I have something to start with so that we can start talking about tools and techniques. The last thing you might do in here before we move on is save your scene. If you remember, saving your scene will save all of the SCs together into one self-contained package. To do that, I go to File, Save Scene, call it Fledermaus, do webinar, and number 2, since I'm doing this again, and click Save. And that will save my scene together. All right, so that's bringing in your core data. Go back to the PowerPoint. All right, so now we're moving on to the real topic of this webinar, the techniques and tools for improved visualization. We're going to start on the techniques end. So techniques that I consider ways to improve your visualization are working with color maps and working with shading. We're going to spend quite a bit of time on color maps. I think they're really important. So your color map, that's the color that's applied to your surface, your SD file when it's created. You can set your color map when you build the SD file. So when I just imported that gridded and ungridded data, I had a space on the wizard where I could choose the color map I wanted to use for import. By default, the color map used by Fledermaus is called Step 16. It's a stepped color map, meaning there's discrete breaks between each color, and there's 16 segments in it. So that's where that name comes from. After you create an SD file, the color is controlled through the color map tab that's associated with that SD file. So here we're looking at a color map tab for one specific SD. Any edits, changes, or information about the color map will all be contained here. So in the color map tab, I can see the name of the color map. I can see that it's a step 16, that it's a percentage type of CMAP. I can see the range of my data. This data goes from -1 to about 73. I can see the spread of the data, and that's this histogram here. It shows me where I have more data points. I can see there's a Tools button, which will let me edit my color map and also import color maps. And I can see a Change Color Map button. The color maps that are used in Fledermaus come from our color map library. The color map library is the system color maps that come with the software. So this is what's available to you automatically. And this is the set of color maps that you see when you hit the Change Color Map button. Your color maps are stored in your software folders. So in Windows, that's under C, Program Files, IVS7, Resources, and CMaps. And there's your location on your Mac. I don't know the location for these files on a Linux machine. The reason I'm showing you this, this is where all of your core color maps are stored. And if you have access to this folder, so if you have admin privileges on your machine, when you make a new color map, you could choose to save your color map in this folder. And when you do that, you'll be able to just click on the Change Color Map button, and the color map that you made will be available as an option. So here I have a color map called Erin CMAP that I created, and it's available for me to use just at this really high-level Change Color Map. Now, if you can't save to that folder, that's fine. You can save your color maps anywhere. You'll just have to use the Browse button to then go through and find where you stored your color map. So it's just an extra step. We have two types of color maps in Fledermaus. We have what's called a percentage-based color map and a fixed-range color map. Fixed-range color maps, when you look at your color map library, they are denoted with an _D after them. So here we see _D color maps, and these are our fixed range. And here we see color maps that are percentage-based, so no _D. Looking at these color maps in more detail over here, this is a percentage-based color map. So I've zoomed in on the top portion of that color map, and you can see that the color breaks are in percentages. So this first color break goes from 0 to 6.25% of the data. For a fixed range color map, you'll note that it says there's a check in the radial box for fixed range up here. Fixed range color maps are scaled to ranges of the data. So here, looking at this zoomed in portion, I'm looking at a color block that goes from -10,000 meters to -9,500 meters. So those are our two types of color maps in Fledermaus. All right, so now focusing on the percentage-based color map. Each color in this color map is assigned to a percentage of the data. So it doesn't matter what the range of your data is. When you use a percentage-based color map, you'll always use the full color map. All right, so here we're looking at my topo lidar ASCII data. And if you look at the data range, it goes from -1 to +73. And if you look at the color map, it goes from purple to pink. Down here, we're looking at my Consberg bathymetry data, and that data range goes from -27 to about -3. And again, the color map goes from really dark purple to pink. So it doesn't matter at all what your data range is. You'll always use the same color map, and it'll be broken up based on percentage of the data. So what that means is that blue here has nothing to do with blue here. They're not equivalent. When you look at a scene that's been created with a bunch of SD files all using percentage-based color maps, you can see that you start to get a bit of a mess. Your scene doesn't make visual sense. So when I'm looking at this scene, this is topography and this is bathymetry, and I can't really tell that by looking at them unless I got in closer in 3D, because rainbows don't really tell me anything about what this data is. Also, I can't compare this purple to this purple, or this blue to this blue. Even though they're the same shades, they mean different values. The second option for color maps is what's called the fixed range color map. So when you use a fixed range color map, each color block has a defined height or depth range. So the full range of the color map may not be used for a particular data set, but you can scale a color map to fit an entire range of data sets across multiple SDs. So here, I've created a color map. I've used our system color map called GMT globe_D. I've rescaled it from -75 to +75. When I apply that color map to my topo lidar data, I see that this data goes from -1 to 73, and I'm using the green to pink portion of the color map, and you see GMT globe. Here I'm looking at the bathymetry data, -27 to -3, and I'm seeing blues, and that's the bathymetric, the negative portion of this color map. It's the exact same color map, it's just been scaled to my data range, and it's a fixed range color map. So 15 here means 15 meters. -22 here means -22 meters. So fixed range color maps work much better if you're displaying multiple DTM SDs together. So here I have my topo lidar data, my Consberg data, and it's starting to make more visual sense. The trees are greens and browns, which makes sense to me. The bathymetry is blue, and there's no overlapping colors that don't mean the same thing. If I were to see blue in this portion of the data set, I would know that they were the same thing because I had applied a fixed range color map to them. One issue with these color maps is that with a fixed range color map, especially the ones that are created in our color map library, they were created for a very specific range of data. So here we're looking at the GMT, I believe it's GMT Ocean, yes, the GMT Ocean color map. And this is the default values for this color map. This color map was created to go from -8,000 meters to 0. I've applied that color map to my data, but my data only goes from -27 to 3. And it just so happens that that range of data fits into just one portion of this color map. So the result is that my SD is completely white. Now, that doesn't mean you can't use these fixed range default system color maps for your data. It just means that you're going to have to rescale them. And you can rescale them using the color map range down here. If you want to edit your color maps, you can do that by going to the color map tab, Tools, and Edit CMap. And that will bring up the color map editing table. In the color map editing table, you're going to be able to do things like rescale the range. So that's what was done down here. You can edit the colors, so you can physically click on each of these colors and change them. You can do color blends using the blending modes. You can edit the range values by clicking and typing in here. You can edit the total number of nodes, and each of these rows is a node. You can create new color maps, and you can save the color maps that you've created. Finally, you can also import color maps, and you do that using Tools, Import. There's a really nice online resource for downloading some free color maps in the GMT format, which is one of the formats we support. The resource is called CPT City. You can just do a Google search of it, and it's the first one to come up, or this is the URL. If you go to CPT City, it brings up this interface where each of these lines takes you to a different page that's chock full of different color gradients for different purposes. I clicked on the IBCO color gradient, and that brings me to the download area for that color map. And I can download it in the CPT format, and that is the GMT format that we support. All right, so now go on to demonstrating color maps. I'm just going to quit my Skype so that it doesn't interrupt us anymore. All right, and back into Fledermaus. So now we're going to start looking at color maps and applying color map techniques to all of these data sets. So to start with, if we take a look at this data, it's a mess. Color-wise, it's just too much to look at. If I click through each of these files and look at their color map tab, I'll see that I've applied the step 16 color map to each of these, and that's our default color map. And again, it's percentage based. So here, in the Reason 2000 data, I'm looking at a data range from -30 to 0, purple to pink. In the Topo LiDAR, -1 to +73, purple to pink. And the Consberg, -27 to -3, and also purple to pink. So the same color map has been applied to each, and it makes no visual sense. We can't tell if these trees are at the same height as this bathymetry. It doesn't improve our visualization at all. We set the color map when I brought these SDs in and when I built these SDs. So in the build wizard, there was the option to set the color map, and I left it at the default of step 16. Looking at the color map tab, again, this is the data range here, so this will tell you the range of that particular SD file. This is the color map itself, so we're looking at the breaks between colors. The type of color map we're looking at here is a stepped color map, so there's very specific breaks between each color. Here's the histogram for the data, so we're looking at the spread of the Reason data set. If you want to change a color map, you can click on the Change Color Map button. We'll get there in a minute. And under Tools, you could do things like Edit Color Map, save images of the color map, import color maps, export to ASCII, make it into a dragging scales color map, or change the histogram so that it's, instead of being blue, you can make it colored by the color value for that section. The first thing you might do is change your color map. So when you click on the Change Color Map button, that will launch our color map library. All right, so this is where all the system default color maps are. Just to reinforce where that data is stored, if I go to my computer, see Program Files, IVS 7, Resources, see Maps. That is where all of your color maps are located, okay, on a Windows machine. So if you're able to access that folder, you can choose to save any new color maps you make there. And if you do that, then when you click on the Change Color Map button, your color map that you created will be easily available at this top level. All right, so it just makes your life a little bit easier. If you can't get in there, it's fine. You can save your color map in a folder or a project folder somewhere and just use the Browse button to find your color map. So the first thing we could do to improve this visualization is change all of the color maps for all of these data sets to be fixed range so that they'll use the same color map that's set for the same range of data, and it will make visual sense. So what we're going to do is we're going to set the color map to these to our system GMT globe _D color map, a fixed range color map. I'm going to start with the Reason data just to orient you when I talk about this stuff. This is the Reason file. The Topo LiDAR surrounds the outside edges of the Reason data. That's the topography. And then the Consberg data is the offshore. So starting with the reason, I can go to change color map, and instead of using one of these percentage-based color maps, I go to one that has an underscore D. All right, and we're going to choose GMT globe and say OK. Now you'll see what's happening here is that it's only using a portion of the color map, right? So if I go in now and say Tools and Edit CMap, we'll see that the GMT globe color map goes from negative 10,000 meters to positive 10,000 meters. All right, so it covers a really broad range of data. And our data fits right in here in this one segment, and that's why it's all white. Come back to the color map editor. We're going to change that by rescaling this color map, but first I'm going to go through and apply that color map to my other two data sets. So my LiDAR, change color map, GMT globe, and Konsberg-Bathy, change color map, GMT globe. All right, so now the same color map has been applied to all three data sets, and though it's not really much to look at yet, I at least see that the trees are green and that the bathymetry, though it's all white, at least I know that white equals white here. The next step to improve this visualization is to take that fixed range color map and rescale it so it fits our data. So I'm just going to take a look at the data range for all my data sets to get a good idea of what I should rescale this to. If I look at reason, that goes down to negative 30. The LiDAR goes up to positive 73, and the Konsberg goes down to negative 27. So the full range of my data goes from negative 30 to about positive 74. And what I'm going to do, I'm going to rescale my color map, and I'm going to kind of broaden out that range a little bit. I'm going to make it fit data that goes from positive 75 to negative 75. So going back to the reason data set, I'm going to go into Tools and Edit CMap. So what we're doing now is we're opening up the GMT globe fixed range color map. You'll see that the fixed range radial key is checked, and we're going to start to tweak it or edit it to make it fit our data. So our data doesn't go from negative 10,000 to positive 10,000. It only goes from negative 30 to positive 75. I'm going to change the color map range down here, and again I'm going to make it even on both sides, and what that does is maintains the zero break. Because this color map is even on both sides, there's a negative 10,000 and positive 10,000, there's a break directly at zero, and we want to keep that. And the easiest way to do that is to maintain even numbers on each side of the break. So negative 75 to positive 75. I hit rescale color map to range, and now I have negative 75 at the top and positive 75 at the bottom. So this color map is better suited to my data. All right, so what I'm going to do now, I can press apply. And if we move that aside and take a look, we'll see the reason data has been recolored with that color map. I'm going to save this color map because now instead of going through and manually editing the color maps on the other two data sets, I can save this color map and use it for my other data. So save CMap file as, and I'm going to save it in that library that I just showed you. So C program files, IVS 7, resources, CMaps. And I'll call it Portsmouth colors 2. And save. Now I've saved the edits I made to that color map, and I can just go through and apply that to my other two data sets. So I say OK to get out of the color map editor. Click on my next data set. Go to change color map, and because I saved my new color map in my system library, it's available right here for me to use. So I can click on Portsmouth Colors 2, say OK, and load that up. And then I can do the same for the Konsberg. All right, so already our data set looks a lot nicer. Things make visual sense. The trees are green and brown, the water is blue. You can kind of see what's going on here. So that's how you can use fixed range color maps to improve your data. To finish up the section on color maps, I want to show you the other tools that are available in the color map editor to let you manipulate your color maps. So we're going to bounce back into the color map editor by going to Tools and Edit CMap. Alright, so you'll see up here you have the option for percentage based or fixed range color map. You can make any color map you want into either option. So if I started with the step 16 here, I can just flip that over to a fixed range color map by checking the other radial button. Other things you can do in the color map editor, if you wanted to edit these colors, you just double click on them and that will bring up the color map selection. You can use any of the colors in these boxes. Whatever is loaded in this box when you say OK is what's going to get loaded into your color ramp. If you don't want to use the basic colors, you could pick anywhere in this selection dialog to choose new colors. And if you're picking colors in there and they're all black, that's because your gray slider is too far down. So just bump that back up and then you'll be able to pick pure colors. So I'll pick a magenta-y purple. Say OK. And that color is now changed in the color ramp. If you want to change values for the start and end range, you can similarly click in there, click in that box, and just type a new number. So I can make this go to 70. And it will adjust the range as well as the range in the next block. Some new tools that we added in version 7 are these blending modes, and these are quite nice. These let you do 2-color blends. The way that works, so if you wanted a color map that went from purple at negative 70 to green at negative 45, I can set up the 2 end colors. Then I left click and holding my left mouse button down, I select all of the color blocks. And then I hit the blending mode. And that will make a nice 2-color blend between those 2 end members. So you can go through and do section at a time by blending 2 end colors together to make a nice gradient color map. The option I just used is called the smooth blending mode, and that makes a nice smooth blend. You can also do a stepped blend or banded blend, and that will show very different breaks between the 2 colors. Let's try and talk about that a little bit. If I go out of the color map editor, and if I zoom in on my Consberg dataset, you might be able to see that there's quite a distinct break between these 2 colors. It's not really obvious with this data set. It was quite obvious with our step 16. But you can also see down here in the color map itself that there's distinct breaks between groups as well. So it's definitely a cut at 11.25. When you have a smooth color map, it blends all those shades together. So going back into the color map editor, if I go up to the portion of my ramp where I have data, and if I say I make negative 30 green and 0 yellow, and I do a smooth blend between those and apply, it's mostly green, starting to turn a bit yellow up in there, but that is a smooth color map. Let me see if I can make that a little bit better. Let's make it more obvious change, green to red. Oh, sorry, I didn't blend. All right, so that is a smooth blend. It's just a continuous blend between colors, and there's no sharp breaks. If you do a stepped color map, let's do this again. I'll go green, dark green to purple, and this time we'll make it stepped or banded. All right, now you can see, looking down here at the histogram and the color map, very distinct breaks, and you can see in some of the colors, you can see where they change. There's a definite edge to the color. Alright, so that's how you can use some of the color map editing tools to make a color map. Some other things you can do in here, you can create all new CMaps, and you can also edit the number of nodes that are available. So by nodes, what I mean is, when I look at this color map, I have 45 distinct breaks or nodes for the data, and that's a lot to deal with, especially if you're planning to edit this color map. You can right-click and delete rows, so I can insert or delete here and just go through and get rid of extra rows that way, but there's a slightly faster way to do it. I'm going to leave the editor, and I'm going to bring back my Portsmouth color map. Now I'm going to go through and edit this so that there's fewer color breaks. Go to Tools and Edit CMap, and I'm going to go to the New CMap button. With the New CMap button, you have the option to create a completely new color map called Uninitialized, and that's going to make a blank color map that you could fill in. Or you can take your existing color map and just change the number of nodes or breaks that are available. My data goes from -75 to +75, and that's 150 units of data that are covered. I can break 150 into 10 classes of 15, so nice even breaks at 15 each. So to do that, I can type in 10 for my number of nodes and say OK. And so what that does, instead of having 45 different breaks in my data, I have 10. You always have 2 extra, one for less than and one for greater than. So that's a quicker way to make fewer classes to deal with if you're going to be editing data, something like that. If you do the new CMap and say uninitialize, again we'll do 10 nodes, that will give you a blank color map that you can then go in and add the colors that you want. Alright, so that's the color map editor. I'm not going to apply any of those changes. The last thing I want to show you is how to import a color map. So I downloaded a color map from the CPTC website. So let's just go there quickly. If I type in CPT city, first one that comes up is the one you want. So bring that up. And in here, you can select on any of these sections and get a whole bunch of color maps that are available for download. I went through earlier and downloaded the IBCO color map. So you bring up the color map you like and you click on the download you want, and you want the .cpt, which is the GMT color map. And that will just download a tiny little file to your hard drive. I downloaded this earlier, so all I have to do to bring it into Fledermaus is go to Tools, Import, GMT, go to my color maps folder, and choose the ibco.cpt. Alright, and once it loads, it will bring in your color map. By default, it will be a fixed range color map, and you see that we're only using a few of the shades of blue that are available. If I go to Tools and Edit CMap, I'll see the full range for this IBCO color map, and this is quite a nice one. So you could rescale this one as well to make it fit your data better. Alright, it's sometimes easier to go find a starting color map like that on CPT City and then edit that rather than start from scratch. Alright, so that's it for color maps. Minimize Fledermaus and bring back our PowerPoint. The next bit of functionality I wanted to cover is shading. I consider this another way to tweak your data, a technique for improved visualization. Anytime you create a DTM SD, a terrain model SD, we shade it by default on build. And the default parameters are always out about coming from the northwest. The sun angle is about halfway up over the horizon. And these are the lighting parameters that are always used. You can edit them and choose whichever option you want by going to the Shading tab, changing these options, and hitting the Shade button. Shading is really important. It can really make or break your data. If you have good data, it will probably look nice no matter how it's shaded. If you had some problems in your data collection, then the way that you choose to shade it can make it appear much worse than it actually is. This is actually some pretty messy data, so not a great example, but it's pretty obvious to see how errors are made worse by the shading. Here, I changed the sun angle so it's going 90 degrees through the lines, and it's really hitting these line offsets right on edge. And what that does is really darkens up the edges and really draws your eye to the place where we have line offsets here. Not very nice to look at. In this example, I've changed the sun direction so that it's going 90 degrees to the line. And what that brings in, or 90 degrees along the line, I guess, what that you start to see there is the pitch and roll artifacts in the line. So they are way more obvious here than they were over here. All right, so just a quick demonstration of shading. For each object, you have a shading tab. So clicking through each individual object, they all have a shading tab associated with them, and all of them have been shaded using the default parameters. I'm going to mess around with some shading on this Consberg data set. So you select the object that you want to change the shading for. You go to the shading tab, and then you can manipulate the different controls. This triangle, yellow triangle, controls your sun direction. So you can left click and drag that around to change the sun direction. This will change the sun angle over the horizon. So you can move that slider up and down, and this little caret will visualize the kind of shadows you're going to show. So with a really low sun angle, you get really long shadows. To see any of the changes, you have to hit the shade button. So if I change my azimuth and sun angle and hit shade, we can see that the surface darkened up quite a bit, and we can see because I hit it so hard at 90 degrees to the line, we can definitely see an offset between the lines. A little bit of an artifact there. If I change it to 90 degrees facing across the line, then we start to bring out the artifacts in the other direction. So pitch and roll artifacts will start to come into the visualization. So the moral of the story is if you're trying to make your data look nice, don't hit it at 90 degrees to either the line direction or perpendicular to the line direction or parallel, because you're going to bring out artifacts. 45 degrees is nice. However, if you get data from somebody else and you're checking for artifacts, then it's a good idea to bring it in and try sun illuminating it at 2 orthogonal angles to see if there's some errors that you could pick up that weren't so obvious before. So that's your lighting direction and your angle above the horizon. Under options, you can reset the parameters to the default and reshade if you end up screwing it up. Or if you get a set of parameters that you really like, you can save those parameters and then reload them for all your different SDs. These lighting parameters make really minor changes to the SD surface. The ambient controls the amount of light, so it makes it slightly brighter. The specular will make the surface kind of plasticky. The soft shadow is the difference between shadow and not shadow. And the vertical scale will pseudo-exaggerate features so they cast longer shadows. What that one means, when you have a feature like this little spot here, if you bump up the vertical scale, it will act as if this feature was higher and therefore make it cast a longer shadow. The difference between vertical scale and sun angle, when you put a low sun angle, it will also make things cast long shadows, but it tends to darken up the entire scene. This will draw more attention to features without making the whole scene overall dark. The easiest one of these to see is specular. So if I bounce that up and hit shade, you'll be able to see what happens with the specular. So by using a high specular, it is like shining a really bright light on the surface, and it gives you high points of reflection. Those are the shiny bits there. I don't really like a high specular, but it's the easiest one to see. The rest of these you really got to play with to get a feel for what they do. It's not really all that obvious. So not a big fan of the high specular, so I'll go back to my last. All right, so that's that for shading. Back to our PowerPoint. All right, from here we're going to go on to the tools that are available in Fledermaus. So in Fledermaus, under the Tools menu, you have quite a few tool options that are available. Today we're going to focus on contouring, surface difference, and attaching a scalar to the surface. To do a contour, you select the data set that you want to contour. you click on Tools and Contouring, and that will launch the Calculate Contours window. The range that's available in this window will match the range of whatever DTM file you selected. When you do contours, you have three options. You can do quick intervals, either bathymetric or topographic. You could do custom intervals where you actually type in the values that you want and the interval step. Or you can insert a single contour at a particular point. And you can use one of these options or a combination of these options. Whatever is listed in this contour intervals box when you hit OK will make a contour. You can also choose to label your contours, and the label size is in height of the letters in units of the data. So if you're working with UTM data, the height of your letters is in meters. If you're working with geographic data, the height of your letters is in decimal degrees. And that's quite difficult to think about. So I usually start, when I'm dealing with UTM data, if it's not a very large area, such as my Portsmouth area, I might start at 10 or 20 meters, see what that gives me. If you're dealing with geographic data, you have to think about those numbers in decimal degrees. And just remember that 0.001 is about 100 meters. And go down from there. Once you create contours, they become an SD file, a line SD, and they can be exported as XYZ, DXF, DWG, or KML. All right, so now to demonstrate the contouring. We're again going to focus on this Consberg dataset. So you select the dataset you want to contour in your datasets list, and go to Tools and Contouring. All right, so you see my elevation range, and that is the elevation range for the selected DTM. I can click on the quick intervals for bathymetry, and what that will do is just generate a couple of intervals. It will be slightly different depending on your data range, but it's put a contour interval every 5 meters for this data set, which is reasonable. If I didn't want a particular one, I can click on it and say delete, and that will get rid of that interval, or I can clear all to start over. If you want to create your own custom intervals with a particular interval step, you can use this section. So you want to set this up, and you can round up and down, but you have to remember to type in the negative if appropriate. So the minimum value for my data is -27. So I'm going to say I want my data to range to start at -30. And that's okay. You can round. My ending value I'll put at 0. And I want a 2-meter step. Set that up and click Generate Intervals, and it will generate a contour every 2 meters for the range of data that we have. You see there's no -2 and no -28 because that falls outside of this data range. The third thing you could do is insert a contour at a particular area. So I can say maybe I want a contour at -5. I can say Insert Contour and type -5, okay, and that will add just a single contour at -5. So you can use one of these or a combination to build up a nice set of contour intervals in here. Then you can choose to label it by clicking on the label contours, and then set your label size in units of the data. So we're going to try and do 10 meters for this data set. Say okay. All right, and when you're done, you'll see that you have a new data set in your data set list. It's called Contour Consberg EM3002. See the contours themselves, and if you zoom in, you'll start to see the labels. The place to look for labels is on the edges of the data set. So right there, we have what's beginning to look like a -22. The bad thing about labels in Fledermaus is that they are flat in a 3D world, so they get covered by the bathymetry. If I turn off the Consberg data and turn off my bounding box, you can see very clearly the -22. But when I turn the data back on, it obscures part of the contour. The way to improve that, if you click on the contour SD file, go to the data attributes and go to the offset and just lift it up a little bit. That will bring the contours up just a little bit so that you can see the full label. Now if you get in and look at this from an angle, you'll be able to see the offset, right? But it does improve the visualization of the labels. So just a choice you might have to make to improve how your contours are visualized. And once you create these contours, they're in SD. Right now they're just saved on memory. They're not saved as part of my scene. As soon as I save my scene, they would be saved. You can also right-click and save the object, save it as an SD, or you can click Export As to export your contours as XYZ, DXF, DWG, or KML. All right, so that is contours. The next tool I'm going to demonstrate is called the Surface Difference tool. What the Surface Difference tool does is it takes two surfaces, usually separated by time. So a surface, a multi-beam sonar surface that was surveyed and created in 2001, and then a second surface that was surveyed and created in 2002. So time has elapsed between these two surfaces and there's been change to the seafloor, so they're slightly different. This will take those two surfaces and it will calculate the Z difference between the two overlapping surfaces. You can also do a surface difference with a surface and a plane. So instead of comparing two surfaces, you can put a flat plane in at a certain height and then run the surface difference from that plane to another surface. And what that will tell you, that works well if you're doing dredging operations and you need to see how much material is above the draft for the vessels coming into your harbor. When you run a surface difference, the order is surface of interest minus reference surface, and that will equal difference. The order that we usually use is to have new surface minus old surface. And that's easy if you have actual surfaces that were collected at different times. You can also restrict the surface difference operation using a polygon, and I'll show you that. And there's two things that you can generate from a surface difference. You can generate a DTM SD, also called a surface object, or you can create a scalar SD. DTM SDs are the things that we've been looking at so far in Fledermaus, a terrain model of values. If you make a DTM SD of this, it won't be a terrain model, but it will be a 3D model. If you do a scalar SD, that's slightly different, and we haven't really talked about scalar data yet, so I'm going to review that. In the IVS world, scalar data equals any data where the third value, or the Z, quote-unquote Z value, is something other than height or depth. So examples of scalar data sets are data sets of slope, rugosity, which is a measure of ruggedness, temperature data sets, difference values like we're doing with the surface difference, anything where there is a third value that is not height or depth. When you have scalar data as ungridded or gridded data sets, you bring those in and create a scalar SD on import. The resulting scalar SD is slightly different than the DTM SDs that we've been creating. They're visualized differently. When you create a scalar SD, it's completely flat when you look at it in the visualization. And when you scroll your mouse over it, you'll see that in the geocoordinate area, you have an X and Y, but your Z will always equal 0. And then you'll have a fourth value, which says scalar. And that's saying that the value of that grid there is 3.48. In this case, we're looking at a slope grid, so that's the slope in degrees. So back to the surface difference. Like I said, you can create a DTM SD or surface object, or you can create a scalar SD. This is worded not quite correctly. This is not a scalar SD. It's a DTM SD or a surface object. So when I ran the surface difference operation, I chose to save a surface object. This is what it looks like. It's a 3D model of difference values. So when I scroll my mouse over this, if you look at the geocoordinates listed down here, you have X and Y and a Z value, but the Z is not the depth of the bathymetry. That's the difference between the two surfaces that were used to create this. With it, you also get a resulting stats window. And the good point about creating the surface object option is that the resulting stats will include volume. So in here, we can see the volume information. So if you need that information, you're going to have to run this type of surface difference. The other option is to do a surface difference and save it as a scalar object. So here it's slightly different. The Z equals 0 in your geocoordinates, but there's a new value that's listed, and that's the scalar. And again, this is a flat grid. Negative thing about this option is that you don't get the volume information in the surface stats. The good thing about a scalar is that you can take a scalar and attach it or drape it onto a bathymetric DTM-SD, or topographic if you're working in the positive land-based world. So you can take it, attach it to a surface, and make it part of that surface. If you like this as a visualization option, but you need the volume, there's no reason that you can't run the operation twice. Alright, so now on to our surface difference demonstration. We're going to be looking at the reason data. So this one over here. I'll turn off the other data sets so they're not distracting. And we're going to have to bring in another SD to compare to this. So I'm going to open another data set that overlaps the reason and was collected at a different time. I'm going to open data object. Bring it in a file called Newport South. Alright, so this overlaps the reason data. It was collected using a different sonar and in a slightly different time, a year later from the first data set. Visually, you could see that these data sets are slightly different. The blue is on top here, so that tells me in this area I have slightly more data in the older data set than in the newer one, so there's been some erosion. Over here I'm seeing the new data set on top of the old, so there's probably been a little bit of deposition there. You can't make too many calls like that based on this because you do, when pixels are the exact same Z, they'll tend to fight with each other who's on top. But you can make some general observations about what's going on. We're going to use the surface difference tool to get actual calculations between the two surfaces. Alright, so again for surface difference you need two overlapping surfaces or a surface and a plane. You go to Tools and Surface Difference. The first surface you want to select is the surface of interest, and as the wizard says, this is usually your newest surface. So we'll take the data set from 2002. Click Next. Now we want the reference surface, or at this time you can choose a plane. For the reference surface, we want the older one. We're going to go with reason 2001. Now if I wanted to compare a surface to a plane, instead of selecting a surface, I would just check this box to select a plane at a height. Here's my setup, so my surface of interest minus my reference surface. Click Next. You can choose to do all data, which we're going to do. You can also choose to just show the calculations above or below, so that will just tell you positive changes or negative changes in the data sets. You can choose to constrain the area that you run the surface difference operation on. We'll do that in a second exercise. We'll run through this again, but this time I'm going to choose no constraints. And finally, do you want to produce a surface object, which is your DTM SD, or do you want to produce a scalar grid to attach to another object? We'll start with the surface object, and then I'll come back and run it as a scalar grid. Click Finish. When it's done, you get your surface statistics window. You can see here you have your volume change information, area change information, and some basic stats. If you want to save this, you click Save As, and it will just save a little text file that you can put in a report. You also create a new SD object. And if we take a look at this, this is a 3D terrain model of difference values. All right. It kind of looks like the bathymetry. It has the sand waves, but it's floating way above the bathy. And if we turn off the bathymetric data sets and just look at the surface difference, you see when I scroll my mouse over it, if you look in the bottom left corner at the geocoordinates bar, you'll see that there's an X, Y, and a Z, but the Z is not a bathymetric value. That is the difference at that cell between surface 1 and surface 2. You can also profile over this, and you see on the x-axis or the y-axis that these are difference values, not depths. All right, so that's when you create a surface object. All right, let's run this again and create a scalar. So Tools, Surface Difference, and I'm going to do the exact same operation, just save it a little bit differently. So Newport South, Consberg, use all data, no constraints. This time produce a scalar grid. Again, you get your surface stats window, but you'll see there's no volume information here. You can save as to save it as a text file. And now we'll take a look at our scalar grid. Oh, I ran that wrong. Sorry. I used the wrong data sets. I used the Consberg and there's no overlap. So let's do that again. Tools, surface difference, Newport, Reason, use all data, no constraints, scalar grid. Okay, much better. Again, no volume information. This time, instead of getting a 3D object, we get a scalar grid. So a scalar grid, again, is flat. When I look at it from an angle, there's no dimension to it, no z dimension. When I scroll my mouse over it, if you look in the bottom left corner, you'll see that there's x and y units, a 0 for the z, and then a scalar value of negative 0.16, or now it's 0.18. And that's the difference value at that cell. Okay. The scalar grid can then be draped on top of an object, and we're going to do that after we talk about importing scalar data. All right, so back to our PowerPoint. So that's how you do a surface difference. The last thing I want to talk about is how you can bring in and create scalar SDs from other types of scalar data. We just created a scalar SD using a surface difference operation. You can also import scalar data as gridded or ungridded data. So you use the import gridded data or import ungridded data wizard, but when you get to the last screen, instead of choosing the sonar DTM or surface DTM option, you'll choose the scalar option. You can also create scalars using the calculate rugosity or calculate slope algorithms. These are in DMagic. So if you're running DMagic and you run these analyses, you can choose to create standalone scalar files for each of those. What you can do with a scalar once you bring it in is attach it to the bathymetry. And what the attaching does is it physically melds or molds the values together, combines the values from both data sets into one SD file. So here I've draped or attached the scalar information from the surface difference to the Newport file. If you look in the geocoordinates, now you have x, y, and z and scalar. So it's taking the values from both files and combine them together. I also then recolored this to make better visual use of the surface difference values, and I'll show you how to do that. All right, so now we'll do a demonstration of importing scalar data. Before I bring in the scalar file, I'm just going to show you what the file itself looks like that I'm going to import. So if I go to my computer, my data files, in my gridded data, I have a text file that has slope information. So I'm going to open that in UltraEdit just to show you what it looks like. Alright, so what we have here is just a typical XYZ file where we have our latitude and longitude in the first two columns. They're in UTM coordinates, so I know it's projected data. But then in my third column, where you typically have your bathymetry or topography value, I have really small numbers, and these are degrees of slope. Okay? So instead of being a typical XYZ grid where Z equals depth or height, we're looking at an XYA grid where A equals slope. The attribute equals slope. All right, so back into Fledermaus. I'm going to import and import gridded data. I go into my gridded data folder and I'm going to choose my Consberg slope XYZ file. This is just straight ASCII XYZ data, so it is ASCII gridded, but you can have scalar data in any of these options, any of our typical standard gridded data formats that we support. You click Next. You set up any variable information. This is an XYZ file, so that's the type of data it is. There were no header lines or data values that needed to be skipped, so I can leave that alone. This is where you set up your Z, X, Y, and Z mapping. If you remember, when I looked at that file, there were only 3 columns, X, Y, and Z. Z is actually A, or slope. If there were more than 3 columns, if you had a text file that had 5 or 10 columns in it, what you would want to do here is make sure that you set it up so that the proper columns are being mapped. We will always assume with an ASCII file that X, Y, and Z are columns 1, 2, and 3. If that's not the case, you just go and select the field that's appropriate. I only have 3 options because there's only 3 in this data set, but if you had more, they'd be available for you to choose. Click Next. You set the input coordinate system. My data is in zone 19. I just know that because I created it. Click Next. You let it do its scan. Once the scan completes, you see the dimensions of your data, and you'll see in the Z value that these are obviously not bathymetric values. They're not negative, and this isn't topography, so these are my slope values. Click Next. We don't have to do any inversion or defining a Z range. You set your output coordinate system. Because my scene is in zone 19, I want my final SD to be in zone 19. Click Next. Set the output SD type to scalar. You give it a name. So I'm going to stick with the default name, but I'll give it the extension of 2. I made one of these earlier. You can change the color map if you want it to. This is the important part, though. You want to create a scalar SD file, not a sonar or surface DTM file. Click Finish. Alright, and we have a new SD file in our data objects list. If I hit the Z hotkey, it will zoom me to my new file. What we have here is a flat scalar file. So when I look at it, there's no Z dimension to it, showing slope. So when I scroll my mouse over it, and you look in the bottom left corner, you see X and Y, the Z equals 0, and the scalar is the slope factor where my mouse is. Alright, so what can you do with these scalar grids? The cool thing to do with them is to take them and attach them to your surface. So this scalar corresponds to the Konsberg bathymetry underneath. If I make the slope slightly transparent, I can start to see through to the bathy. Alright, what we want to do is take the slope value and attach it or drape it onto the bathymetry grid. Alright. To do that, you click on the scalar grid, the scalar SD, you go to its scalar attribute tab, and you say attach to surface. The surface you want to attach to is the corresponding bathymetry or topography. So I want to attach it to the Konsberg EM3002 bathy. And then you have 2 options. You can just attach the scalar, and what that's going to do is take the scalar values and stick them on to the bathymetric grid. So when you scroll your mouse over it, you'll see the 4 values, but visually the grid will look the same as before. The second option is to attach those scalar values, but then also shade the surface by the scalar. So color the surface by the slope values instead of the bathymetric depth values. I'll start with the first option so you can see what it looks like and say OK. Alright, so no visual change, but if I turn off my Konsberg slope and focus on just the Konsberg bathymetry, visually it looks the same, but when I scroll my mouse over it, if you look in the bottom left corner now, instead of just having X, Y, and Z, it has the X, Y, and Z, so the Z being the depth value of the bathymetry here, and then it also has a 4th value, which is the scalar, and that's the slope value at that cell. Alright, so that's the first thing you can do. The second thing is you can then color the surface by the slope values. Now I could have did that in one step by checking that second checkbox, but if you don't, you can do it now as a second step. To do that, you click on the SD that has the attached scalar, so the Konsberg EM3002. I go to the Shading tab, and I click Color with Attached Scalar. Hit Reshade. Alright, and so what it's done is it's gone through and it's trying to color the surface based on slope value. Unfortunately, it's using a color map that's not appropriate. It's using that IBCO map, so the colors don't look nice for a slope. But we can fix that. We just go to the color map tab, and this time we might change color map and use one of our percentage-based color maps instead of a fixed range. So I'm just going to pick colors in terp. Alright, so now what we see happen is instead of coloring the bathymetry by depth, it's coloring it by slope. We're still visually looking at the bathymetric values. They've just been colored by the slope values. And when we scroll our mouse over it, we can also get the actual slope value down in the bottom left corner in the georeferencing bar. Alright, so that's how you can attach a scalar to a bit of bathy or topography to make one data set with more information. Another thing you can do here that we didn't talk about, you can set a user range on a color map to restrict the color map ramp. And what I mean is, right now I have slopes that go from 0 to about 60, but I don't have very many slopes at 60. There's probably just 1 or 2 spots in here that are the color red. Most of the data is down here under about 11 degrees. Alright, so all of these colors aren't being really used in my image. To try and tighten that up, I can restrict the user range. You can do that manually. I can just click the little down arrows here, and you'll see that my color ramp is adjusting. The faster way to do it is I can put my mouse where I want the color ramp to end, so right here about 11, and I can right click. And that's going to tighten up the user range. Then I hit apply, and now it's going to recolor the color map based on the user range. All right, and I'll know that anything that's bright pink is outside of 11 degrees. You can use that trick on any color map. It just works really well for scalar type of data sets. All right, the last thing I want to do is go back to the surface difference. So I'm going to go back to the rezon area. Now, one thing I forgot to show you is how to do a surface difference and restrict it with a polygon. So we're going to run one more surface difference with these two data sets. To restrict the area that's used in the surface difference calculation, you can use one of our polygon select tools to draw a polygon on the surface of the area of interest. So I'm going to use the area select tool to go around part of the sand wave. Now when you do this, you want to make sure to only get areas where there's complete overlap. If you go outside, if I go all the way down here, it won't run properly because I'm outside of the area of overlap. So I'll just get my area select and do a really quick selection on part of the sand wave field. Then I can go to Tools and Surface Difference. I want to use my new port, compare it to my rezon, use all data, but this time I want to constrain it using the polygon selection. I want to produce the surface object this time around, but you can also produce the scalar and click Finish. Alright, so we get our set of surface stats, and we also get just a portion of an SD file showing the surface difference. Now it looks a little bit bigger than the outline there. That's just your visualization perspective. If we get dead on to these edges, you'll see that you're inside the edges. You just have to take into account the 3D nature of your perspective. Alright, so that's another surface difference operation. To finish up, I want to show you how you can do the attached scalar with that surface difference scalar we created. So we're going to focus on the Newport South bathymetry and the scalar data grid we made showing surface differences. And what I'm going to do is attach this grid to this bathymetry. So I select the surface scalar, or surface difference scalar, go to its scalar tab and say attach to surface. And I want to attach it to my Newport South. And this time I'm going to choose to shade the surface by scalar after attaching. So I'm going to combine those two steps into one. Alright, once it's done, I can turn off the scalar. And now that that scalar's been draped on top of the bathymetry, the color map's just not very nice. So we're not seeing good colors. We're just going to adjust the color map to improve that. But you see when I scroll my mouse over it that I have x, y, and z, and then also the scalar value. And in this case, the scalar is the difference between this surface and the other surface. A nice way to color a scalar or an attached scalar is using something in the color map editor called the Create Positive Negative CMap. So I'm going to show you how to do that. Alright, so to edit this color map, I select the bathymetry because remember, we're focusing on the bathymetry now. The scalar data has been attached. Click on the bathymetry, go to its color map tab, and I'm going to go to Tools, Edit CMap, and then I can right click and say Create Positive Negative CMap. This works really well for surface difference data because you tend to have positives and negatives where you've had deposition or erosion. Alright, so I have positive and negative values, and this will break them up very nice visually so that I can easily see where there's been deposition or erosion. This will break it up nicely, make solid color on either side of the zero. You can change these colors to be whatever you want, but I'm just going to stick with the green and red for now. I'm going to say OK. Alright, so now I have a piece of bathymetry. I've attached scalar data to it that's showing the difference between this survey and an earlier survey, and I've colored the bathymetry based on whether there's been positive change or negative change. When I scroll my mouse over it, I also get the extra value of seeing how much difference there was between this survey and the last survey by looking in the lower left corner at the geo information bar. Alright, so that is how you can use the attached scalar as part of a surface difference. Alright, so that's it for this webinar. I'm going to get my PowerPoint back up. Just finally, if you have any webinar questions or requests, you can email me, eheffron@ivs3d.com. However, if you have bugs, license issues, or anything like that, please email support. You can contact them through our website, ivs3d.com, support, and there's a little link to contact support. Or you can just send an email to support@ivs3d.com. Thanks again for attending this webinar, and hopefully we'll see you at webinars in the future.